Okay, sorry, I am a minute late. There has been various issues today, but let me just get this set up. And okay, good. Okay, so let's talk about what again, the important topics for today. One, we've got a midterm coming up on Thursday. I'd like to talk about the backtracking problem, and I'd like to talk about dynamic programming some more, and then hopefully any questions you have. So today is kind of a, sort of a little bit of a catch-up, catch-all class. First thing to tell you is about the midterm. The midterm will be on Tuesday, correct? The midterm will be, just like the other midterm, a three-ish, real problems, and a collection of 30-ish multiple choice problems. The four chapters that we're covering are going to be, the graph traversal, weighted graphs, backtracking, and dynamic programming. I will pretty much guarantee you that the written problems will all be pretty obviously traceable to the to homework problems in the book. So not necessarily the ones that are on the assignment, but I think that an excellent way to study for the dynamic programming problems are to do the dynamic programming problems from homework 5, okay, which is assigned, and I encourage people to do that. Any questions about the midterm? Yes? What was the question?
Will each of the short answer problems be a dynamic programming problem?
Will each of the short answer problems be a dynamic programming problem? No. There's going to be, I have, unfortunately, 4 chapters to cover, and unfortunately, only 3 written problems on here. So figure that there will be 1 from every kind of chapter. Okay, so I don't want you to, I do want you to figure out dynamic programming, but if you haven't figured out graph algorithms or backtracking, this is a good idea to try to figure out. Any other questions about the midterm? Okay, fair enough. Okay, the first thing I'd like to talk about, just to catch up, is we ran the backtracking problems, the contest. The homeworks, remember what was our backtracking problem? Let me lower the volume a little bit. What was the backtracking problem here? The backtracking problem this year was our set cover problem, as we remember. And there were a total of 5 programs submitted for the backtracking contest. One thing, I'm trying to decide how do I want to say how they did. What I will say is that I don't want to give you names unless people really want, okay, for the people who didn't win, okay? But one program, okay, was actually pretty good, but got one of the examples wrong. Another program was good, except it got a couple of programs wrong. Good meant fast, wrong means bad, okay? Why would wrong answers come up? A wrong answer would come up if you came up with a set cover solution that was bigger than it was supposed to be, right? The thing that made your program run fast was it had to search through essentially all the possibilities in order to be competitive, okay? The guarantee that it got the best possible answer. Pruning means eliminating some possibilities if they are not good enough, okay? If they can't possibly lead to a better answer. Over pruning is when you eliminate something that can lead to a better answer. And so typically the ones that I'm going to guess, we didn't diagnose it, that the couple that were submitted that for a few answers gave examples too big, they were presumably over pruning in some way. Bottom line is that there were two programs that survived, okay, until the end. One of them got slow at, what you call it, of the two winners that I'm going to declare two winners this year. One got slow at the random graph 733-100, and at the, what you call it, the one that I guess we called the K-type graph at 175. Another one was capable of solving all the problems except SK 150, 250. And these are the two that I want to declare as co-winners. So if Jason Chung and or Greg Zaborski is here, I'd like you to come on down. Do we have a Jason Chung? Do we have a Greg Zaborski? Okay, we have a Greg Zaborski. Okay, fine. So he will win the prize. I want to give so first we'll give him a round of applause. Second, I've been pretty discombobulated. Do you have a pen?
Nope.
Okay, I'll sign it at some point. What is the most valuable prize that one can give on, the answer is, of course, this book. But more than that, I'd like to have a quick discussion about this. Why was your program so fast? This is the question now. So the way I'm thinking about it is, again, we were doing backtracking, it was set cover. What was your solution vector? Let's stop to think about it. What was your solution vector? What were you storing, the form of your solution?
A list of subsets.
Tell those people. It's a list of subsets. So you're telling me that you were going to say subset 1, subset 2. These are going to be your solution was going to be a set of subsets.
Right.
And you're presumably accumulating things. Is this right? In the course of your backtracking.
Right.
You were adding more and more things. Under what pruning did you do?
There were several avenues of pruning that I took. One was I think the one that most people got was if you ever find a minimum solution, never go further than that.
Okay, so what you said, just to be honest with you, suppose you had a solution. You have a solution, subset 1, subset 17, subset 23, subset 64. You have a solution of size 4, okay? You're saying that whenever you had put down 4 elements, okay, if it hadn't, if you were building up your solution one subset at a time, if you ever had put down, a 4th element, you know that this subset has minimum size 4, it can't possibly beat the best that you did. That's what you're talking about, right?
Right.
Okay, so part of this is, would you under this case put down element 4, or would you give up earlier?
I would give up on the previous one because we don't care about finding a solution of the same size to our minimum. We only want smaller than our minimum so far.
Does everybody see that if he had a solution of size 4, okay, once he had put down 3 elements, if this wasn't a cover, now you can give up. Anything you add to this is not going to give you a better solution, okay? So that's one area of pruning to do, okay? Were there other things you did?
Another one of the optimizations that I did was a little bit dependent on the order in which I added subsets. So I added subsets not just based on the subsets themselves, but I looped over every element that needed to be added to my final set cover, and I enumerated all the subsets which needed to be added to them. And then one idea was that I would sort my I would sort these elements on the number of subsets that covered them. Thus, elements which had few subsets covering them would have few branches at the root. So if we can cut off any one of those branches, we'd have massive amounts of pruning. So that ordering was just one good way to get a bunch of...
Okay, so let's be precise here. So first of all, we could have done this thing where we were trying to build these things up where the subsets were just given in their input order, right? Now tell me, how did you order those subsets?
So instead of ordering the subsets, I ordered elements instead. And then from each element, I ordered subsets, and this actually causes an issue where you go over where you can, for example, go over subset 1, then subset 2, and at a later point, go over subset 2, then subset 1. But I came up with other optimizations to get rid of that.
Okay, so what he's saying is he did his backtracking a little bit differently than the way maybe I taught in here, where I told you to come up with basically, you know, an ordering of all the subsets, okay? Notice that the ordering of the candidates, again, if you think about what we were doing with backtracking, actually, to fill the next slot, we had to construct candidates, okay? We had to think, those were all the possible choices here that we want to explore. You're arguing that some you want to explore sooner than others.
Yes.
Okay? And what is an example of something you might want to explore? If you had only 2 subsets, let's put it this way, if you had only 2 subsets that included the elements 5, let's say that subset 1, A and C, were the only subsets that included element 5, you knew you had to include one of either of these 2, right? So I think that what you were saying is that you would prefer the order of subsets, the ones that you thought of as for the next slot. You prioritize them based on what elements had been. Okay, a couple of different ways. Did you prioritize them based on what was already covered? Meaning, if I had already had, let's say, subset C here, 5 was taken care of. Now I have no need to cover 5, right? So A may have seemed important in the abstract because it had a rare element. But once I had picked an earlier one, it was no longer as rare. It was no longer valuable for that rare element in the future.
Right. So I would take the subset with the greatest number of remaining elements to be covered.
Okay, so that was now his criteria was, he would order the elements here, he would take the union of everything that he had so far, okay, and said, I have a certain amount of work to be done, okay, and based on this, now all the subsets that he hadn't picked yet can be interpreted based on how rare or, you know, basically how much more work they have to do. So he took the set difference between every subset and what was already covered. And now there was a power to cover the remaining subsets. And he ordered these things from most powerful to least powerful. Is that correct?
Right.
Okay. Any questions about that? That's a perfectly reasonable thing to do. My guess is you did some other things. Okay, what other things did you do?
There was another 1 or 2 or more optimizations related to the way that I ordered my elements rather than subsets. One of those was that you could early exit on the number of elements, for example, rather than exiting 1 element early, based on the way that I would choose subsets to cover the next item. I could exit 2 early instead of 1 early. And this doesn't seem to make a massive difference.
Okay, so what you're saying here is he would like to make the decision to give up, not one move before he was the best one he had. It would be great if he could make up a decision to give up earlier. Okay? Is it possible that you could make a decision to give up? Let's say that the best one that we know of was of size 5. Let's say I'm going to now have S73 in this one. We filled in these 3 slots, okay? There are 2 slots to go, okay? Is it possible for me to give up knowing that this prefix can't help me achieve something. Let's say even the best strategy I had was of size 6. Let's say S at 95, okay? Let's say the best I know of is size 6. Is there any possible criteria by which I could give up after I've only got a partial solution of 3 subsets? Okay? And I'm going to argue there is. Suppose, let's say, that there were 100 elements still uncovered. Right? And let's say after you did your symmetric difference, that shrunk the effective size of all the remaining sets, right?
Yeah.
Because you deleted anything that was already covered. Suppose the largest of these remaining subsets had 30 elements. Do you see what I mean? Suppose you knew that there was a solution of size 6, okay? Your prefix right now had covered all but 100 of your elements. And you knew that each of your subsets could only cover at most 30 new elements each. How many subsets do you need to finish the job? You could only get at most 30 new ones, 30 new ones, 30 new ones. By the time you filled it up to size 6 with this prefix, you would still have 10 left over. Do people, I don't know if that's what you did, but do you see that there is a grounds to make a decision based not only on the number of subsets that are the best solution you have and how big your current solution is? You can estimate how much work you still have to do, and you might be able to make a decision earlier. I'm going to claim you had some way of making an estimate of this.
I actually didn't see this. I had a more naive version that only went down to 2.
Okay, so you're saying that you had something that didn't look quite as far ahead as mine, what I proposed, but it looked more than one spot ahead.
Right.
Right? And again, the hope would be that the better pruning would happen, the earliest you could do it. And the moment you could prove that a particular subset was, prefix couldn't improve what you have, that's when you give up, and there's no candidates for that. Anything else you did? I guess you did some other things too.
I removed, and with the idea of maintaining your sets, but with the union elements already removed from those sets, we can apply the idea of taking subsets and not considering them if they're a subset of any of our other subsets.
So what you're telling me is so long as, like if you had a subset of the element 1 and a subset that was the element 1 and 5, the subset, the element just 1, couldn't possibly be useful, right? So I assume some of you guys, a lot of you guys probably pre-processed your subsets and checked if one was included within the other, right? Certainly whenever you saw an empty subset there, you should not have been very excited about considering it as a possibility, right? And did you do that pruning only at the beginning? Or did you do that dynamically as you went on? Once you'd simplified this, did you look at these, the remaining subsets after you stripped them, to see if what's left is a subset of the other?
Dynamically, yeah.
You did it dynamically. So if, let's say, you had a subset here, I'm going to call it, let's say that we had a subset 1, 2, and a subset 1, 3, okay? And these are both possibilities. If I had put element 2 over here, if element 2 was part of S2, this would have gotten knocked out now from your consideration. And this was a subset of this, right? So that's not just changing the order of the candidates. He's reducing the number of subset candidates at each spot. The branching factor is going to get lower that way. This, I imagine, was a big win.
Yeah.
Okay? Anything else that was done?
data structure rather than with pruning itself. This one was mostly a constant time optimization, although it did give like maybe a roughly 5 to 10x speed up, which was
Okay.
using a bit set rather than a regular set. So almost all the operations were much closer to like O of n divided by 60.
Okay, so what he's saying, I think, is how do you represent what a subset is? Okay? One way to represent the subset is as an array or a linked list of elements. 1, 3, 5. Right? What I think he's saying is, I'm going to represent this by a bit vector. If the maximum number of elements, my universal set, if my universal set was, let's say, 64 or less, I could represent any subset by a bit pattern on 64 bits. That would be one word, one integer, okay? And I'd be able to represent an entire subset with that. Does everybody kind of get that idea? He could, if it was 128 elements, his integer would be a bigger thing. And now he's manipulating integers, basically, to do set operations. Okay? How do you union two sets then? It's like a bitwise AND. Does everybody see that? A bitwise OR.
Yeah.
How do you look for the ones that are in common to both? That would be a bitwise AND. So do people get the idea that if you're clever, there are these bit representations for subsets? This is a little bit dirty, okay, but not so dirty. Bit vector is a perfectly rational thing to be dealing with, okay? And he said it made a constant factor improvement in the program, okay? And that I can kind of believe, okay? This was not the first thing you did. This was hopefully the last thing you did.
It was one of the first things just because it makes a lot of the operations easier to implement as well.
Okay, let's say it's a good thing to see, okay? Any questions about how the bit vector worked? Yes?
Did you use C++? Yeah, so in C, I used C++, so they had the built-in STD bit set, and the way that's implemented internally is it's just a C flat array of as many important integers as you need to represent whatever value you want to represent. Although you could have totally done this in Python or Java or anything else like that as well, but maybe with a little bit of overhead.
Okay. The truth is that at least when I was looking at this at one point, one of the fastest programs submitted was in Python. Some of you guys said, oh no, I got to program bare metal, yada yada. He got a factor of 10 by programming, this bit vector thing closer to bare metal. What he won by was he reduced his branching factor by eliminating these unnecessary subsets at every point, and by looking ahead more than one spot. Okay? Any other questions about how this was done? Okay, give him a round of applause and then go. And if you have a pen, come by my office with a pen sometime, I'll sign it. Okay? But don't sell it on Amazon before you do. Okay, good. Okay, any other questions about, Any other questions about the backtracking and how we did that? Okay, good. Okay, let me, okay, if that's good, I'd like to now talk a little bit about, get back to the dynamic programming stuff. Any other questions about either backtracking or dynamic programming or the exam? Anything? Okay, the daily problem, sorry. No, not this one, no. The problem of the day is not the one that is on the screen, but it's a little bit close to it, I believe. Okay, but let me read the one that's on the screen. From 1032 is what I remember. And the daily problem has to do with typing on a keyboard where basically it's like a piano. So we've got a keyboard here. Let me erase this. we have a keyboard, like a piano keyboard, and there are the letters A, B, C, D, dot, 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 up to Z. There are the digits 0 through dot, 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 9. There's all the punctuation symbols you want in the world, period, bang, dot, 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 filling out the rest of my keyboard. I have a message I want to type, Watson, come to me, which I think was the first thing said on a telephone, if I am correct. Okay? And you want to type out the message. Okay? And you have 2 fingers. And the question is, what is the most efficient way to type on the keyboard with 2 fingers? Is this what people understood the question of the daily problem to be? Now, suppose, let's say I've got 2 fingers here, and my message was AB, 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 AB. What would be the most efficient way to type it with 2 fingers? Yeah? I should have A here, B goes here, go pop, 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 pop. Does everybody agree? If it was AZ, 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 it should be something like pop, 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 pop. Right? But the speed of typing is a function of the movement, how long it takes me to move my finger back and forth. Right? And the question really is, if I only had 1 finger, is there any question about the most efficient way to type something? No, because I would go W, kabunk, A, kabunk, T, kabunk, right? When I've got 2 fingers, do you see that I want to plan where my fingers should be in order for me to type it? Now, what should I do if my message was, and again, I wish I'd stretched my keyboard out. Let me put the capital letters over here. Sorry about that, I'm not happy with that pen. Suppose I had my capital letters all the way out here. Suppose my message was AB, AB, capital Z, AB, AB, capital Z. What is the most efficient way for me to type it? It's probably, yeah, you have a vision?
Yeah, keep your left hand on the AB.
I'm probably should be doing something like pop, 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 bunk, pop, 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 bunk, okay? So there's planning ahead. It's not just do the last 2 characters. Does everybody kind of see that? How would I go and decide the most efficient sequence where I should put my finger to be? Okay? You kind of see what my problem is? Okay? Can we solve this by dynamic programming? Okay? If so, what I need is, to solve something by dynamic programming, I need to have a definition of what function would be useful that if I knew how to compute it, I would be able to solve my problem. Can anybody come up with a definition of a function that if I could compute it would be helpful? This is the first part of these formulations. Any proposal? Okay, I'd like a proposal. Even if it's wrong, I'd like a proposal. Okay? Okay, now when people say hey, they can be wrong, suddenly they're happy to answer. Yes?
So I have like C, I, and A.
So you want, what are you going to call your function? You get to name it. What letter you want to call this function? C for cost. And what are the arguments of this function going to be? I is an index for what?
For the last character.
So I is going to be the position in the string in the text. Is that right?
Yeah.
Okay, what else did I want?
And AB for the left and right.
Okay, how about I call them L and R just to keep me straight? This is the finger position on the left. I think this is what you want, right? Left hand, and this is the finger position on the right hand, right? Okay? Now, what do you want? What is this function doing? That's the argument for it. What do you want this function to store? What is it going to tell me?
The total cost.
It is this is going to be equal to the cheapest cost to type message 1. This is my string. Let me call my string M for message right now. Message 1 through message I, where my fingers end up. On L and R. I know you can't read it, but do you hear what I'm saying? I think this makes sense to me now. Right? C of ILR is going to be the cheapest cost to type the first I characters of my text, where my fingers end up on L and R. Okay? If I knew how to do this, okay, if I could compute this, what is the answer to the cheapest way that my, the cheapest way that I should end up? Okay, if I could use this, how would I find the optimal cost overall? The cheapest way to type it? Is this going to help me find the cheapest way to type it? How would I use this to find the cheapest way to type it? Yeah? You're telling me L and R have to end up like this. Do my fingers have to end up like this? I don't think so. Do I care where my fingers end up? I don't think I care where my fingers end up, right? You want me to type the message, yeah?
Is it the minimum between C(I)(1) and the left-hand move, and compare that to the right-hand moving to that same line?
Okay, I think that what I think it is, if I have this function, what is the cheapest one? I think that the cheapest one is going to be C, the cheapest possible cost, is going to be the min, and C of n. If n is the length of the string, it's the min of C of n L R over all L and R. Okay? If I don't care where my fingers end up, only that Watson comes to me. We agree, if I don't care where the fingers end up, the best thing to do is to type the message at cheapest cost, and I know my fingers have to end up someplace. This is going to tell me the cheapest way to end up after every prefix and every possible set of finger positions. Does everybody agree with that? Yes?
So for L and R, one of them has to be the last character, right?
Turns out that you're right that for this to be non-trivial, either L or R should be the last character. So I'm going to say that there is some, that's maybe an optimization. Because you're going to tell me it's going to take longer for me to move my finger after I've typed it someplace else. So you're right. In the winner, either L or R is going to be the last character. Okay? And so that might maybe a faster way to recurrence for solving this. Right? But this is kind of just the end. What I really want to know is the recurrence for computing the big thing, which is there. Okay, any questions about where I'm coming from? Do you see how this formulation is starting to happen? Okay. Now, let's go and work out what that recurrence is. I'm trying to say, where do I want to delete? I'm going to delete Watson coming here. We'll keep the typewriter. We'll keep this here. Does anyone want to give me a recurrence to compute this function? What would it be? Does anyone want to make a proposal? Okay. Anybody see what it means? Okay. And I'm willing to try to come up with something. What would I be thinking about? Well, thinking about it expansively, the cheapest way to type, what should the cheapest way to type the first I characters ending at L and R depend on? Yeah? It's going to depend upon where my fingers were before. Does everybody agree with that? Okay. So maybe what this is going to be is the min over all, I'll call them little l and little r. Okay. Of what? I'm going to claim it's the cost of typing the first I minus 1 characters ending up on little l and little r, plus what I'm going to say is the distance from L to L and R to R. Let's look at what I'm doing here. It should be clear that if I'm typing it, what's going to be happening? Kabunk, I typed something. Kabunk, 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 kabunk. Every time I do this, I'm doing two moves. I can move both my fingers independently, right? How much it costs to move my finger, okay? My left finger is going to go from L, little l, to big L. My right finger will go from little r to big R. Perhaps the cost should be this minus this or this minus this. Perhaps it should be the bigger of the two, right? If I have to move this finger to there, that costs 1 time. If I have to move this finger to there, presumably the bigger of the two, this finger will arrive at its destination before this one does. Does everybody see that I can have a distance that's encoding however the cost of operating a typewriter is? Perhaps people start to move quickly and then slow down if they have to go long distances. They get tired of moving their fingers. Or maybe it's something different. Maybe typically you start moving slowly, but once you accelerate, you're faster at the end of it. Whatever the cost of the movement is captured in this thing. And does everybody see that the cost of doing this, where I end up on this, is the minimum over all previous states, which is defined by where the fingers are, the fact that I already typed out the first I characters, and that I will move this distance. Okay? Any questions? There is still a problem with this formulation now that we come to think about it. What's missing from this formulation? Okay, there is something missing right now that this recurrence doesn't actually capture. Yeah? I didn't actually hit the key, right? So now, how do I capture the cost of hitting the key? Now, this is a little bit trickier if we look at this formula here, okay? Somehow the hitting the key, remember I think I had that my message was called M, was what I seem to recall of doing it, right? So basically, what I think I also want to do is to add a cost that is going to call it as hit of, hit of M sub I. What does this mean? I do have to pay a price for hitting the ith key. Now, perhaps that's, 1 millisecond or something like that. But it seems to me that for me to hit that key, it could be that M sub I is only going to be nothing if either L or R equals high. Does everybody kind of see that? I've got to actually hit the key. In order to hit it, my finger has to be on it, right? So maybe I'm going to expand this to something like L, R. No, I'm sorry. This goes here. MC, right. No, this is right. And I'm going to define that hit of K, L, R is the cost of actually hitting the key. And I'm going to say basically if key K equals L or R, the cost of this will be 0. And if key K is not equal to L or R, the cost of this is going to be infinite. Now what will this do? This means that unless L or R end up at the right, one of them ends up at the right finger, does everybody see that this term's going to cost me an infinite amount? Okay, that's not going to be something I'm going to want to do, right? Instead, this is going to force me that the only values of this that are going to be non-infinite are one where L and R is going to be, either L or R ends up on the right space, and then I get that for free. Okay? Any questions about this? There's different ways you can formulate this. Okay? But I think you're starting to see how a practical problem can be decomposed into a dynamic programming solution like this. Any questions? What is the running time of this thing? Okay. What is the running time of this algorithm? Okay. I need to know how many boxes, and I need to know how much time per box, right? How many boxes are there? Okay. Yeah? What? Is it the length of the string? Well, the length of the string needs to be something. Let's say that the length of the string, we said, went from 1 to n, right? The string was n characters long. Okay, is there any other parameter we need? We need to know how many keys there are on the typewriter keyboard, right? How many keys are there on the typewriter keyboard? What? Okay, you can call it what you want. I'm going to call it K for key, just to keep it, because I like that. Okay? How many boxes are there in our dynamic programming as a function of n and k? Yeah? I'm seeing n times k times k. The number of boxes is equal to n times k squared. And what is the cost per box? What is the cost per box? According to this, I've got to pick my L and R, which are what? Those are where my fingers used to be. L could have been in any one of K places. R could have been in any one of K places. I've got K squared's choices for this. The distance function can presumably be complicated in constant time. The hit function took constant time. Looking this up in a table took constant time. This would be time per box is equal to K squared. According to this, my algorithm is going to run in n k to the fourth. Okay? Maybe there's some optimizations where I don't need to look at all possible things because I know one of them had to be where the finger was before. Okay? So maybe if I'm clever, I could reduce this. But do you see where my analysis comes from? K squared time per box, n times K squared boxes. This is something like n to the K to the fourth. Any questions about that? Any questions about how I did this formulation? Okay? One way or another. Okay, and I'm going to argue that a lot of dynamic programming problems that occur in practice look something like this. And let me now try to prove that to you. I want you guys who are in here to reach into your wallets, and normally people get scared when you say that, but I want you to reach into your wallet and pull out your driver's license. On the back of your driver's license, I claim is going to be a, look back there. You've got this thing on the back of your driver's license. Does everybody see that and believe it? Who here has one of those things on the back of their driver's license? Okay? Now, what is that thing? Okay? That thing is actually your prison record. Okay? That what happens to you? You get caught speeding. What is going to happen to you? The cop's going to pull you over. It says, give me your license. Okay? And they take that license. And what are they going to do with that license? They go back to their car and they scan it on the barcode with this thing. And they look to see what kind of dude they're dealing with. Right? Okay? Maybe all you ever did was get a parking ticket. That's good for them to know. But if they knew that you were a wanted man or if you were someone who had a big prison record, probably you need to treat this guy differently. So this is basically on the back of your driver's license an encoding of your record, okay? Any questions about that? You guys have seen barcodes before. Yes? It turns out it's not an ID. So one thing you might have imagined is that, that it just gives you your ID number, and the cop goes and looks this thing up, and it goes to a database someplace. What happens if this cop doesn't have Wi-Fi where he is? Okay? The cop would like to be able to have the whole record there with you. So this is not your ID. This is your record. Okay? It may have other things in there, I don't know how many of you accumulated how long a record so far, but it's got other details about you, okay? Any questions about that? Yes?
Is it like readable, like human readable, or is it like...
Is this human readable? No, you can't look at that and say, bad dude, okay? But you can, there are decoder programs for this, and that's what the question's going to revolve around. Any questions? Okay? So how do we do this? Well, the company that made this is a company that used to be called Symbol Technologies. It's now called Zebra. I don't know if any of you have heard of Zebra in the area, right? And they developed this two-dimensional barcode symbology where the goal was to get as much text as possible. Some of you guys have pretty long prison records, okay? And they want it to fit on the back of your driver's license. They don't want to have to give you 2 or 3 cards for your driver's license just because you've got a big prison record. So the question goes, given the constraints of scanning, which define kind of the pattern of dots, how do we encode as much text as we can in that label? And it turns out they use the following idea in doing this. Okay? I know because the person who developed that barcode symbology used to be a professor at Stony Brook named Theo Pavlidis, who was... But what was the idea? The idea is that the prison records come in parts, okay? One thing they might want to know is a phone number. You can imagine your phone number might be in this record. The phone number has the property that it's a sequence of digits, right? And you can imagine other things, parts of it, that say, warning, treat this guy very, very carefully. You might want to have in capital letters. And you can imagine other things maybe they want to have in lowercase, and other things they want to, there's punctuation symbols. So how could you encode a message on the back of that tiny little barcode that you have? They chose to do it this way. They could have typed it in ASCII, the kind of character code that you're used to, and that would have 8 bits per symbol. Right? That's kind of what a normal 8-bit ASCII is, 8 bits per symbol. The other possibility is that they broke the letters into different modes, and you can get away with smaller number of bits. There's only 26 different letters, right? 5 bits will suffice to give a lowercase letter. 5 bits would suffice to give an alphabetic letter. 5 bits here, 5 bits here, okay? So if you're going to be encoding a message where you stay in one part of the alphabet, you would get away with 5 bits instead of 8. But sometimes you might want to jump to a different mode. You could imagine that you're typing on your prison record, warning, exclamation point. You then would have to jump to the punctuation mark. Do you kind of get that idea? So expressing a pattern in here is a result of there is a cost in bits to get a letter depending upon what mode you're in. If you're in the alpha mode, okay, in order to type out that one exclamation point, you pay the cost of going momentarily into this, then the cost of typing out the bang, and then you're back in there. Or you might decide that you want to permanently stay in this mode. That's a different command. Maybe the message you want is warning like this. Maybe you want to really shift into a mode. So what do they have? They have latch commands that put you in one mode permanently. They have shift commands to let you go in one character. And there's a cost for outputting something in the right man. So what is the problem that we use dynamic programming for? The question is, if you've got all these complicated ways to type out a message, you could shift here, you could latch here. Latching makes sense if you're going to use it enough later on. How do you know? Okay? They originally had an algorithm that just kind of made guesses and stuff like that. But when they told me about this, I said, wait a second. If you want to find the optimal way to encode it, what if we let's define m sub ij as being equal to the min cost encoding of the text from 1 to I, the first I characters of the text, ending in mode J. Okay? This, I claim, would be helpful. We care about typing ultimately all end characters of the message. We don't care what mode we end up in, right? We don't care if you ended up in a punctuation mode, latched or not, so long as you typed out the whole thing. My claim then, the optimal encoding of your prison record is given by this. M sub ij is the min, okay, over all modes. So min over j, mode j, of where the cost of it is, you had to type out the first, actually it's the mode over all, excuse me, take that back. It's the min over all k of the cost of typing out the first I minus 1 letters ending up in mode k, plus the cost of typing the ith letter and ending in mode j. Does everybody see that this thing, okay, is a constant time thing that depends upon the weirdnesses of whatever the PDF 417 technical spec is, right? If I'm in mode 1 and I want to end up in mode 3 typing it, well, I either have to go, either I can go, I have to type it out in mode 1 and then transfer permanently into mode 3, or I could transfer into mode 3 and then type it. Okay, if it happened, the letter happened to also be there. My claim is the problem reduces to this dynamic program. Any questions? It's like a shortest path kind of a problem. Okay, yes?
So does this search for all K? For all the
This search for all modes, but how many big is K? You have to search over, it writes the min over all K. How many different modes were there? If you look back to my picture here, how many modes did I have? 4. I'm searching over 4 possibilities, right? That doesn't break anybody, does it? Okay? But even if, so long as I had some constant size thing, this is telling me, again, I should probably go back to this again. Boom. Okay? This is the idea here. Do people kind of get the idea of what we're doing? We're able to make our decision, the right choice for how to end up in mode J after typing I letters depends upon the cost of getting to each mode after having typed up K-1 letters, I-1 letters. And then the cost to do the local change, which, if we go back to what we had over here, okay, is some local little distance function, an awful lot like that. Any questions about that? Okay? So what's good about this? Okay, this is what's the running time of this algorithm? Let's think about it. If I have K modes and a text of length n, what's the running time of this algorithm? How many boxes times how much time per box? How many boxes do I have? Kn boxes. And how much time per, per box? K. That gives me something like the running time of this is nk squared. Okay? Where, again, k is 4, so that really doesn't matter to them, right? N is the size of your prison record. Okay, your prison record can't be too big if you're still walking the streets, right? So again, this is something that was perfectly efficient, okay, and it came up with the optimal encoding for them, and it was 8% on average. Our encoding was 8% shorter than the one that they worked on because they had some heuristic of what was greedy and good and making the best decision. So if you do a dynamic programming right and find the optimal cost thing, okay, you can save space or save time or save money, whatever you're looking to save, by coming up with a better solution than just some heuristic. Any question about that? Any question about PDF 417? Okay, fair enough. And so this is I hope by now you're starting to get an idea of what the way you proceed on a dynamic programming problem is. Okay, what do? I start out by defining a function that if I could compute it, it would be good. I then prove it could be good by showing that there was another way of doing this. That if I had this function, I could get the answer to the problem I really care about. I then wrote out a recurrence relation that would do what I want. And then, once I have the recurrence, it's usually trivial to read off the number of boxes and the amount of time. Any questions? Any questions about this dynamic programming thing? Okay, what I'd like to do now, I just give you a quick philosophy on dynamic programming again, just to make sure we're getting it right. One is that, again, dynamic programming is good when there is an order on the things, okay? Dynamic programming is good when we have a recurrence and there are few results to compute, okay? You couldn't use dynamic programming on your backtracking thing because, yes, backtracking was recursive, but you never hit the same state twice. Actually, you're sort of saying your storygram might have hit the same state twice, but it presumably didn't or shouldn't if you did it right. Okay? And if it did, it didn't do it very much, or else he would have been in trouble. Okay? On the other hand, if you've got things that are linearly ordered, you typically have not an exponential number of things to do, but a polynomial number of possibilities. Whenever we have two fingers over n choices, that's n choose 2. Whenever we have a subrange from a certain point to another point, that's two fingers, that's n choose 2. When there is a linear order on the things, like strings, like tree leaves, actually, if they're properly embedded, okay, like a lot of things, if there's a linear order, in fact, you will only have a, a small number of distinct possibilities. When you have something that is linearly ordered and can't be rearranged, okay, that's when I start to smell dynamic programming. Any questions? Okay. Now, why is it that dynamic programming works? Okay, I've been a little bit loose, okay, about my proofs of correctness here. Okay? Dynamic programming works, okay, when something observes something they call the principle of optimality, but that's a fancy word. It means that whatever the initial state is, the future decisions must be optimal to the state from the last decision. Okay? Notice that in there were four, in that barcode example, there were 4 modes. There was a message, okay? The optimal mode I was in when I did the optimal message may have jumped around between modes at certain points. Boop, 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 boop. But if I want to make my next decision, the important thing was, what mattered was not all the stuff that happened here, What happened was the cost of all the stuff here and and the cost of getting from here to there. What makes dynamic programming work is kind of if you can forget how you got to a particular point, but that you got to it. If the cost of what I had to do over here, the cost of the optimal move, depended upon something I had done earlier. Let's say the cost of this depended upon a coupon. And if I'd used the coupon earlier, I can't use it again. I would need to know, did I use the coupon? Where did I use it? But if the cost is only a function of what the state then is, then my decisions are basically made with respect to the state and not the whole thing. And if that's true, as it's been on all the problems we've talked about, that's when dynamic programming works. Any questions about that? Any questions about dynamic programming or anything else here? Okay, according to this, I've got approximately 12 minutes left. I will give you another dynamic programming problem unless one of you gives me a dynamic programming problem. Is there anything from the homework that, let's say, you may have wanted to know how to go about? Okay? Or any of these other problems that you'd like to have a discussion about? Is there anybody who wants to have a discussion about any of the homework problems? From this or anything else or anything like that? If not, I'm going to go back and do some more slides so you guys get a choice. You want me to do any of the homework problems? Going once. Going twice. Okay, no one. Okay, let's go back and look at another example then. Okay, I'm going to go do this linear partition problem. Unless somebody is going to tell me they have a better idea. Any questions? Okay. So let's look at another example of dynamic programming, which is one of the examples in the book that has come up practically for me a couple of times. And it has to do with, suppose, let's say, you have an ordered set of objects. Okay? In this case, let's say that we had, let's say that there was a ransom note stuck in printed on a book somewhere in the Stony Brook Library. The books are on a shelf, okay, are on the shelves, okay? And each book has a certain number of pages to look through. The cost of looking through a book is proportional to the number of pages. Suppose I want to divide the work of partitioning all of scanning through all the books among a certain number of workers where I can't rearrange the books. Okay? So I'd like to divide the library into sectors and say, Joe, you do these books, Bill, you do those, Mary, you do those. What is the fairest way to divide it? Okay? If I have 3 workers and 3 books of 100 and 9 books of 100 pages each, does everybody agree that the fairest way to divide that work would be simply to give three books to each person? Does everybody agree with that? What would be the fairest way, however, if we have books where they go from 100 to 900 pages, 9 books like that? Is the fairest thing to give everybody a chunk of 3 consecutive books? If I'm the manager of the project, I would say that's a great idea. You do this part, you do that part, I'm going to do this part. Right? Does everybody agree with that? What would be the fairest way to divide these books up now? If you have 3 workers, would someone propose a fairer breakdown of this? Yeah, what would you propose? Okay, I'm not hearing that, I'm afraid. If we're dividing up these particular 9 books, what is a fairer way to divide the work? Okay, you're going to put the first divider. See, I have these dividers. Where would you put the divider? Between which 2 books? Okay, so you're saying you'd like to give somebody the first book and the last book. That means that you're rearranging the books. Do you see what's kind of happening now? You're going to be forced to they're going to pile the books around. You're not allowed to rearrange it. I want you to divide these things, divide the shelf up into ranges, where the ranges are as balanced as possible. So this might have been a thing to do. But actually, as you'll learn after the midterm, finding the best way to do that's going to turn out to be NP complete, so we're not going to do that. Suppose I want to divide it like this. Yeah? You're going to put the first divider here, and this next divider where? So what happens? If we do it this way, in the old way, the original way, this guy had 600. This guy would have had 1,500 in the old way, and this guy would have what? 2,400. Now with the division like that, how would that be? So it would have ranged from 600 to 2,400 in the old world. How would it do it under his proposed scheme? The first one is what? The first one's 1,500, right? The second one's 1,300. The last one is 1,700. Does everybody see that that's a much more fair thing? Okay. How do we find the fairest way of doing that division? Okay. If you read the book and the war stories, there's a war story where, in a parallel computing thing, where the guy I was working with did a terrible job of it and got into a lot of trouble. Now, okay, how do we find the best way to do it? I claim we've got the following problem. The linear partition problem says we're given an arrangement of n integers and an integer k, and we want to partition it. And the criteria I want to do is to minimize the maximum sum. Minimizing the maximum sum means that no one guy can be doing too much work, right? If I minimize the maximum sum, then that's going to be the time, if the time that the job ends when everybody can go home when the last guy finishes. Minimizing the largest part is what the criteria should be. Any question about that? That's my goal. So how do I partition this? I claim that there is a recursive idea here, okay, that I want to think about. Let MNK be the minimum possible cost over all partitions of the first n items over k subranges, where the cost is only going to be the largest sum, the piece in the largest amount. My claim is that, okay, M of nk is going to be the min of S of I, k minus 1. What does this mean? If we want to try to come up with the fairest partition of the first n items with k dividers, What is the cost of this going to be if I do it recursively? If I put my last divider here, what is the ultimate cost? What is the biggest partition? It is either going to be the sum of the elements to the right of the last partition, or it's something in a smaller problem. Does everybody kind of see this? If I'm putting down a total of k possibilities, okay, I'm going to claim that there are the biggest piece, if you give me a solution, the biggest piece is either going to be all the stuff to the right of the last partition, meaning the stuff the last guy did, or it is not, somebody else's has the biggest piece. What is this going to say? I want to put my partition, my divider, my last divider, my kth divider, is going to go in some position I. If I put my last position divider in partition I, what's the cost of it? The biggest partition either is everything from the I plus first to the nth element. This is the last part. Okay? Or it is something in the previous problem. Well, if I chose my last partition to be at position I, what do I now have? I'm going to want to know what is the cost of the best possible way to deal with k minus 1 partitions, because I've already used my kth one at position I, to divide the numbers 1 through I. This is going to tell me the biggest piece in the best possible partition to get to the point. This is going to tell me the thing that's to the right of it. Okay? The bigger of these two is what the cost should be. And I want to choose my partition, place, to minimize that. Any questions? How many people sort of see this? Okay? Again, what are the basis cases? What are the basis cases where I know this? What is the cost if I have one book? Okay? One book, and I have k workers. What's the best way to divide the books among k workers if I only have one book? I say, Murray, you get the book, you do it, we'll watch, right? So, if you have one book and a lot of workers, it's still the size of that book. What if you have one worker and a lot of books? How do you divide the work up among one worker? You don't, okay? They get all the work, right? So the other basis case was this one. Okay? That if you have n books and one worker, the cost is doing the whole thing. Any questions about that? Any questions about doing the dynamic programming? My recommendation for learning this stuff, try to find the easiest ones you can do. Okay, if you're looking at these homework exercises and the problems in the book, some will be more confusing than others. Look at the simple ones to try to understand why they work. And then gradually, hopefully, you can get the hang of it.